The next talk is by Jessica Shi, and she'll tell us about theoretically and practically efficient nucleus decomposition.
Okay, cool. Awesome. Thanks for the introduction. And also thank you to the workshop organizers for inviting me to speak here. I'll be talking about theoretically and practically efficient nucleus decomposition. And this is joint work with Lakshman Dhulipala from UMD and Julian Shen from MIT. So I'll also be talking about how do we cluster a graph. So thanks to Vincent and Fahab for already bringing up this topic. But we'll be focusing on a different kind of fundamental idea. So there are many algorithms for graph clustering. But what we'll be concerned about today is this fundamental question of how well connected are certain nodes or groups of nodes in a graph. And in particular, we'll be looking at this classic algorithm known as k-core. So formally, the k-core of a graph is a induced subgraph where every vertex has degree at least k. So you can look at the maximum k-cores of a graph. And there's a very simple linear time algorithm for finding the k-cores of a graph. The algorithm simply looks at the entire graph and repeatedly finds and removes the vertex with the minimum degree. So this is what we call a peeling process. So in this graph example here, the entire graph is a 2-core because every vertex has degree at least 2. And you can see that the green vertex is the vertex with minimum degree. It has degree exactly 2. So if we remove this vertex, what we see is we have these 2 disconnected subgraphs that are each 3 cores because every vertex has degree exactly 3. And that's the end of the peeling algorithm. We don't get any further information from peeling more vertices in this graph. And so in some sense, this gives us a nice semblance of clusters, right? The blue vertices are well clustered with respect to each other. There is a fundamental problem with k-core, however. So for instance, if we have a graph like this, let's say it's a social media graph where we have follower and following relationships, perhaps we have these densely connected friend groups represented by the blue dotted circles, but maybe one person in each friend group follows some celebrity node. So now if we run the k-core algorithm, what we end up seeing is that we would begin by peeling each of the blue vertices because they have degree lower than the green vertex and would peel the green vertex last. And the entire graph is actually within a 3-core, but we don't actually get these nice friend groups out of the k-core algorithm because we don't get any further information. So a solution to this is a process known as s-clique peeling. So essentially, the idea is that we can solve these kinds of problems by looking at higher order structures in the graph. So instead of looking at the degree of each vertex, what we now care about is the s-clique degree of each vertex, or the number of s-cliques that each vertex is contained within. And now the process is exactly the same. We want to repeatedly find and peel the vertex with the minimum s-clique degree. And now in this example, we see that the green vertex is actually not contained within any 3 cliques or triangles, but each of the blue vertices is contained within 3 triangles each. So in this peeling process, we would remove the green vertex first, and what we're left with are the clusters that we want to find, where every vertex is contained within exactly 3 triangles each. So these are the 3 triangle cores. And actually in this talk, I'll take this a step further. We'll generalize this to the idea of nucleus decomposition. So essentially, in the previous examples, we considered vertices as first-class citizens of the graph. Now what we actually care about are r-cliques. So what we're interested in is the r-clique, is the number of s-cliques that each r-clique is contained within. And we'll classify these r-cliques into a hierarchy based off of the same peeling process. So we repeatedly find and peel the r-clique contained within the minimum number of s-cliques. So in this example here, if we set r equals to 2 and s equals to 3, what we care about is the number of triangles that each edge is contained within. And actually the light gray edge is contained within no triangles, while each of the dark gray edges is contained within 2 triangles each. So in the peeling process, we would remove the light gray edge first, and that would give us our clusters, which are the dark gray edges, and that forms a 2, 2, 3 nuclei. And I'll note that the triangle peeling process actually wouldn't give us these clusters in this particular example graph because each vertex is contained within exactly 3 triangles. So the entire graph is within a 3 triangle core, and we don't get any further information from triangle peeling. So that's the definition for RS nucleus decomposition, or at least the intuition behind it. Are there any questions about this?
Wait, yeah, Jessica,
Yes.
can you say again what an RS nucleus is?
Yeah, so essentially an RS nucleus is, I guess, a subgraph in which every r-clique inside that subgraph has s-clique degree at least a k, where you're considering the k-RS nucleus, for example. Right, and where we take s-clique degree to mean the number of s-cliques that each r-clique is contained within. Yes, it's a lot of variables. Are there other questions about this definition? Oh, so the question was, what is the 2 in front of the 2, 2, 3 nucleus? The first 2 refers to the fact that each edge is contained within at least 2 triangles. Okay. Okay, so hopefully this makes some sense. Yes.
So let me ask from beginning. So when you're peeling, are you peeling the edges, or you just entirely remove the vertices of this r-clique?
Yeah, so that's a good question. We're peeling just the edges, right? So we don't remove the vertices, especially if they're connected to other edges that are still existing in the graph.
Good. And this still gives you a subgraph. When the process finish, you have a subgraph that the vertices that have each, like inside each component, each r-clique belongs to S. No, what is going on?
So the subgraph in the end, each edge will belong into at least k r-cliques if it's the k-RS nucleus.
All right, perfect.
Yes.
Thank you.
Okay, fantastic. So I'll motivate this even further by pointing to a nice example from some previous work. So Saryusz, Seshadri, Pienaar, and Katalyrik, some of whom are in the audience today, actually introduced the problem of nucleus decomposition, and they constructed the hierarchy for a lot of real-world graphs, including this Facebook graph with 88,000 edges. So basically what these hierarchies are showing is it's showing the containment of these nuclei, where the nodes of these graphs represent the set of vertices, and the shape represents the size, and the color represents the density. So as you can see, we have some hierarchies for the 1-2 nucleus decomposition problem, or the K-core problem, and also on the right, another hierarchy for triangle peeling. But if we generalize this even further and look at the 3-4 nucleus, you can see that we have a much more expansive and descriptive hierarchy, and also we get many more subgraphs of varying densities than we would from the other kinds of, from the less general peeling processes. Okay. So in this work, what I'll present is new shared memory parallel algorithms for nucleus decomposition that have strong theoretical guarantees. And we'll also implement these algorithms and show that we outperform the state-of-the-art algorithms by several orders of magnitude. And importantly, we'll be working in the shared memory parallel regime throughout this talk. So I'll try and motivate why we should do that, and also why we care about these theoretical guarantees. So throughout this, I'll be using the same machine, a 30-core GCP machine with 2-way hyperthreading and 240 gigs of main memory. This is some commodity hardware that you can get for about $4 or $5 an hour. And so the previous state-of-the-art work by Saryusz, Seshadri, Pienaar, and Katalyrik, they actually have a sequential nucleus decomposition implementation. And they're able to run 3-4 nucleus decomposition on a variety of real-world graphs. So here we have the skitter graph with 11 million edges, the live journal graph with 34 million edges, and the ORCID graph with 117 million edges. And as you can see, they take 8.5 minutes for the skitter graph, just over 3 hours for the live journal graph, and they actually hit our timeout limit at over 6 hours for the ORCID graph. So this is clearly a computationally intensive problem. And one way to be able to bring these running times down and actually finish running on this ORCID graph within our timeout limit is to introduce parallelism. So they actually have a subsequent paper by Saryusz, Seshadri, and Pienaar that introduced several parallel nucleus decomposition implementations that's shown in the light blue here. And they actually can achieve some pretty significant speed ups just with their parallel implementation. So notably on this ORCID graph, they can now finish in 1.3 hours. one way that we discovered to bring these running times down is to introduce theoretically efficient algorithms. So the algorithms that were used in prior work were not theoretically efficient, but we introduced in this work some new theoretically efficient algorithms that when we implemented, we're actually able to bring these running times down even further. So notably for this live journal graph, previously the speedups were not too significant. It went from 3.3 hours to 3.2 hours. But with our algorithms, we're able to bring that down to 14 minutes. So this is sort of the main thesis of this work. And I won't talk too much in detail here about the practical optimizations that we introduced, but we do introduce some performance engineering techniques on top of this, and we're able to bring the running times down even further to 13 minutes for this OR-clique graph, just over 3 minutes for LiveJourno, and 24 seconds for the skitter graph. So great, are there any questions about this? Okay, fantastic. So I'll go on and I'll talk about some of the preliminaries, and then I'll introduce the algorithms that we're actually considering. So if you caught Vahab's talk yesterday, he briefly mentioned the work span model. So here it is again. We use the work span model of computation for describing the theoretical guarantees of our parallel algorithms. So on the right here, we have a parallel computation graph that shows the dependencies between different parallel tasks. The work is the total number of operations or the total number of nodes in this graph. And the span is the longest dependency path or the longest directed path in this graph. And we use this model because we can describe running time. It's upper bounded by work over the number of processors plus big over the span. And importantly, we'll try to create algorithms that are work efficient. So this just means that the work matches the best sequential time complexity. And I'll also use the notion of arboricity throughout this talk. So this is something that Kwan introduced yesterday in her talk. So the arboricity of a graph is the minimum number of spanning forests needed to cover all edges of the graph. You can think of it as a measure of sparsity in a graph. In a lot of real world graphs, it's bounded by polylog n, at least that's the behavior that we tend to observe. And also it's upper bounded theoretically by the square root of m, where m is the number of edges. And importantly, we'll be using this to construct graph orientations. So we define a C orientation of a graph to be a directing of a graph such that the out degrees of every vertex is upper bounded by C. And in particular, what we'll be concerned with are arboristic orientations. So that's just an O of alpha orientation. And actually in our prior work, also by myself, Lakshman, and Julian, we introduced two theoretically efficient arboristic orientation algorithms. I won't go into details about how those work, but we'll be using them in this work. And these are important because they'll give us the work efficient bounds for nucleus decomposition. Okay, so now I'll talk about the actual algorithm. And I'll introduce the algorithm through an example on this graph on the left. And what we'll be concerned about with is 3-4 nucleus decomposition. So we're looking at triangles as first-class citizens, and we're concerned about the number of 4 cliques that each triangle participates in. So this is how the algorithm works. The first thing we do is we direct the graph to obtain an arboristic orientation. So you'll have to take my word for it that this is an arboristic orientation. And then we'll use a clique counting algorithm to count the number of 4 cliques per 3 clique or triangle using this directed graph. And we'll store these counts in a bucketing structure. So essentially in this graph here, the triangle CDG is contained within no 4 cliques. There is a 4 clique between the edges A, B, E, and F. So every triangle in that 4 clique, except for the triangle ABE, is contained within exactly 1 4 clique. And then you can see that there's a 5 clique A, B, C, D, E, all triples. And that set are contained within exactly 2 4 cliques, except for the triangle ABE. And finally, the triangle ABE is contained within 3 4 cliques. So this is our bucketing structure. And now we proceed with the peeling algorithm. So we start by peeling the set of triangles with the minimum 4 clique count. So initially, that's just the triangle CDG. And then we update the 4 clique counts of the remaining triangles. In this case, nothing has to be updated because CDG was contained within no 4 cliques. And then we repeat this process. So the next triangles to get peeled are all triples in the set ABEF, except for the triangle ABE. And then when we update the 4 clique counts of the remaining triangles now, we see that the 4 clique count of the triangle ABE should be updated since all of the other triangles in its 4 clique was peeled. So in fact, we move that now to the 2 bucket. So now all triangles remaining have 4-clique degree exactly 2. So now we essentially peel the rest of the triangles from the graph, and we're left with an empty graph, so we're done. So this is the basic nucleus decomposition process. And so I won't go into the bounds for the first 2 steps in a lot of detail. These are from prior work by myself, Lakshman, and Julian. But essentially, we can construct the arboristic orientation in O of m work and log squared n span. And we can perform the clique counting process and m alpha to the s minus 2 work and s log n span with high probability. So what I will talk about in this talk is how we accomplish these other 2 subgoals. The first is that we need a way to keep track of which triangles or r-cliques are mapped to which bucket or the number of s-cliques. And we also need to be able to extract the minimum bucket efficiently. And the second subgoal is we need a way to update the s-clique counts of the remaining r-cliques after we've peeled a set of r-cliques. So this is what we'll be focusing on. I'll talk about the first subgoal first, and then we'll move on to the second. So the first subgoal is we need a way to keep track of the r-cliques with the minimum s-clique count at every given step. What we actually use theoretically is a batch parallel Fibonacci heap that was developed in prior work by myself and Julian. So this can support k insertions in O of k amortized expected work and log n span with high probability. And also it can extract the minimum bucket, so the set of all r-cliques with the minimum s-clique count, and log n amortized expected work and log n span with high probability. Although I'll note that in practice, Fibonacci heaps are not efficient. So we actually use a bucketing structure known as Julienne that was developed by Lakshman, Kai Bullock, and Julian in 2017. And there are some other practical considerations that we had to work on in relation to this bucketing structure, but I won't have time to go into details about that in this talk. So this gives us the bounds for this first subgoal. It takes O of m alpha to the r minus 2 plus rho log n amortized expected work. I'll note here that rho is the number of rounds that we need to run this while loop to completely peel the entire graph. So actually this problem is p-complete. We also show that s-clique peeling specifically is p-complete in prior work. So it's unlikely that we'll remove this rho log n dependency, or it's unlikely that we'll be able to get polylog n span. So our span is rho log n span with high probability. So now I'll move on to talking about the second subgoal, where we want to update the s-clique counts of the remaining r-cliques. So in theory and in practice, we basically show a key lemma that improves upon the previous best theoretical bounds for even sequential nucleus decomposition, which I'll talk about here. And in practice, we also include some other software optimizations that I won't have time to talk about. So let's talk more about this key lemma. Essentially, the way that we accomplish this subgoal is we modify the s-clique counting subroutine to efficiently obtain updated s-clique counts from the peeled r-cliques. And this will allow us to update the s-clique degrees of the remaining r-cliques. And in particular, we prove this following theorem, where over all c-cliques in a graph, the sums of the minimum degree of each c-clique is upper bounded by O of m alpha to the c minus 1. And basically, we show this with a clever counting argument. So why is this theorem useful? Well, this is the basic algorithm for updating the s-clique counts. So let's say that we're peeling some triangle, say ABE, which is shown in pink here. Essentially, the way that the argument works is we first want to intersect the neighbors of every vertex in this triangle. So here we're considering undirected neighbors, so we don't care about the directing of this graph for now. And that gives us our set S. So our set S is the neighbors of A intersected with the neighbors of B intersected with the neighbors of E. And this gives us the set CDF. And then in parallel for every vertex in this set, what we'll want to do is we want to intersect the arboristically directed neighbors of the vertex that we've picked with the entire set. So for instance, let's say that we pick this vertex C. Well, we only have to look at the arboristically directed neighbors of C now, and its neighbors are D and G. And if we intersect it with the previous set S, we receive this new set, which is just the vertex D. And then we repeat this process with the new set S, which just contains the vertex D. And we can see in the next step that basically there's nothing to intersect with because the set S only contains one vertex. And actually, if we take the set of all of the vertices that we visited in this recursive process, we see that that forms a clique with the original set of vertices that we peeled. So we peeled the triangle ABE, and then we've added C and D, and we've discovered the 5 clique A, B, C, D, and E. And the arboricity process allows us to avoid double counting. So we won't rediscover this 5 clique if we go through other threads in this recursive process. And this is basically how our update process works. And now to talk about the bounds in a bit more detail, essentially this theorem allows us to upper bound the first step where we find the intersections of the degrees the intersections of the vertices in every r-clique that's upper bounded by m alpha to the r minus 1. And then we multiply this with the factor of alpha to the s minus r minus 1. And this is because of the arboricity orientation. We only have to iterate through the arboricity directed out neighbors of every vertex. And so in total, this gives us m alpha to the s minus 2 work. And this is actually a nice result because m alpha to the s minus 2, if you recall, were our work bounds for s-clique counting to begin with. So the bounds for the peeling process actually match the original bounds just for s-clique counting. So this gives us our total work bounds. We have m alpha to the s minus 2 amortized expected work from the Fibonacci heap for this last step with rho log n span with high probability. And if you sum this all up, our total bounds are m alpha to the s minus 2 plus rho log n amortized expected work and rho log n plus log squared n span with high probability. So are there any questions about the nucleus decomposition bounds or theoretical guarantees? Yes.
So in some of the applications of orientations, you can replace the arboricity orientation with the degree orientation, which is just easier to compute. Is it possible to get all these bounds with the degree orientation?
No, it's not. Basically, I think you might be able to get so if you remember the update step, you might be able to get the bound for the first one using the degree orientation, but you really need the arboricity to do these efficient intersections to get the rest, right? So the issue with the degree orientation is that I think it's efficient for certain small clique counting because essentially you can prove that it leads to an arboricity bound. But to do the intersections, you really need the out degrees to be bounded by alpha.
So it isn't possible to sort of amortize the cost over all intersections?
Yeah, exactly.
Also, Jessica, I had just a clarifying question.
Yeah.
What is the randomness over in this algorithm?
Oh, so basically we use a lot of hash tables. So parallel hash tables usually give the randomness. Yeah, so that's kind of obfuscated, but that's hidden in the Fibonacci heap and also other aspects. Okay, cool. So I didn't have time to talk about fractal optimizations, but I'll just quickly mention that we implement a lot of fractal optimizations that give us up to a 5x speedup over our unoptimized parallel code, and also up to a 2.5x reduction in space usage over our unoptimized parallel code. And I'll also very quickly talk about the experiments. So we use a 30-core GCP instance with two-way hyperthreading and 240 gigs of main memory. And we also use real-world Stanford network analysis platform graphs. So this graph shows our multiplicative speedups of our parallel code over the previous state-of-the-art parallel code by Sarius, Seshadri, and Pinar. So they actually introduced 3 implementations called AND, NN, and PND. And we take the fastest of each of these implementations for each graph. So as you can see, we get some pretty significant speedups, especially for this live journal graph, which goes up to a 55x speedup. And the median on average is about a 9x speedup. We see very little speedups for the YouTube and Amazon graphs, in particular because their fractional optimizations have too much overhead to be really useful for these small graphs. So I'll note that the Amazon, DBLP, and YouTube graphs all run in under 3 seconds. So this is just our speedup numbers again. We also see up to 40x self-relative speedups, and we tested this for r less than s less than or equal to 7, as our code is general for any values of r and s. And mainly our speedups over prior work is because prior work is not either has large span or is not work efficient, or it runs out of memory. So it's not space efficient. Cool. So in conclusion, I've showed that shared memory parallel clustering algorithms developed with strong theoretical guarantees and using practical optimizations can be efficient and scalable. And there are many future directions for other work in this area. So there are extensions that you can consider with respect to nucleus decomposition specifically, for instance, dynamic and approximate nucleus decomposition, which has been done in the setting of K-core. And there's also other generalizations that we could consider for other graph classes, such as bipartite graphs. So all of our code is publicly available at this link, and I'm happy to take any questions.
So if we only wanted to answer the query whether two vertices are in the same nucleus decomposition or not, do we know whether that can be done significantly more efficient? Are there any existing bounds?
I don't think there are bounds that I know of, but my intuition is the answer would be no, that you could probably show a similar p-completeness result for that as what we show for. So basically what we show is a p-completeness result for whether like the nucleus is empty or not. So I assume it would be similarly hard.
Okay, makes sense. Thank you.
I'm curious about your empirical results.
Yes.
There's a very impressive speed up for LiveJournal and for ORCAT, which I think is kind of a similar graph. The speed up is very different. So I'm curious what made LiveJournal specifically. What do you think why do you think it performs so well there?
Yeah, so LiveJournal basically has a structure that allows for many vertices to be PO'd in the same round. So I think most of the speedup comes from the fact that we reduce the number of peeling rounds necessary. And then you can get a lot of speedups just from the parallelism within each peeling round, right? So it basically has this kind of like dense hierarchy structure where you can get a lot of nodes in the same like core PO'd at the same time.
Thank you.
Okay, maybe let's thank Jessica again. Oh, okay, let's do one more question.
Yeah, hi. What's the space overhead here? Like what exactly are you storing and what do you have access to?
Yeah, so I didn't talk about a lot of the practical details. There's actually some considerations in how to store the r-cliques because storing many r-cliques is computationally expensive, and you can reduce that by storing the overlaps of certain r-cliques instead of like repeating all of the vertices for all of the r-cliques. So that's really the space overhead. I also didn't talk about algorithms that consider using space proportionate to the number of s-cliques, which can be more efficient than this. So the regime that we're considering is space proportional to the number of r-cliques.
Thank you.
Okay, I think we'll thank Jessica again.